playing. Thanks for being here. So I'm going to talk a little bit today about a pretty simple, low-tech, low-effort, but seemingly impactful intervention that I had done in a class related to helping students hopefully have a better conceptual grasp of stress and strain and stress strain curves and what that means. Um, but right, that's a pretty specific, narrow application. I think maybe a subtitle or another title of this talk would be an example of how to find, take some troublesome bit of knowledge that students seem to struggle with and figuring out some way of designing some kind of hands-on activity so students can make connections between words on a slide and things that they can experience and maybe understand in real life. So there's a little bit of background. So my very first semester here at RIT, I was teaching a biomechanics course that our students take in their second year. And I would imagine, like most BME biomechanics courses, this is the kind of hodgepodge of statics, dynamics, and deformable materials kind of smushed into a single semester. Right? So it necessitates kind of going quickly through that process. Not at all an area of interest or anything I had done since I was a student. So I had this textbook and I was excited to tackle it. And we made it through all of the statics and dynamics section. I got to deformable materials and I'm introducing the concepts of stress and strain. And the textbook has these really great graphs, right? It's saying here you have this material, you have it in 3 different dimensions where your cross-sectional area or your length are different. And if you were to deform them, right, apply some force and measure their change in length, you would see that all 3 of these different specimens have different deformation curves. And therefore, you can't really draw any information about the mechanical properties because you're intermixing the mechanical properties and the geometries of these objects. But hey, if you do this thing where you normalize to geometry and you convert force to stress and you convert change in length to strain, all of a sudden now these 3 different curves converge, and now you can extract information just about the material and not about the material plus the shape that you were looking at that moment. And I'm like, great, super clear, pictures, slides. Students are definitely going to understand this. And we go through the standard homeworks where they're calculating stress and strain and, doing whatever. And then on the final, I had a question, which was, how would the stress strain diagram of a metal shaft change if the diameter is doubled, but the material and testing conditions stay the same? This is going to be a super easy, simple question for these students where you just say it stays the same because stress strain only depends on materials plus testing and not geometry. And I got about 25 to 30% of the students got this correct. A lot of students who are, jumping into the equation for stress, like, stress is inversely proportional to area. So if the area goes up, then stress has to go down, right? If you double the diameter, the same force, your stress is going to drop. So the curve is going to be lower. Right? Lots of students who, plugged in numbers to try and figure out what this was going to be. And I think this is definitely a problem that I have noticed is students frequently get into the kind of pattern matching of here's an equation. This problem mentions something about this equation. I have to use this equation. I'm going to plug in numbers and see what happens without necessarily really understanding what that equation is really trying to say or what is the context for using it. And so after this kind of first iteration, I said, you know what, I don't want the students to just view this as a math problem where here's an equation, plug in numbers, see what happens. But I wanted them to really kind of understand the concept of why we use stress and strain, what it means. This idea of it allows you to normalize to different geometries so you can compare materials across different kind of situations or environments. As I was developing this, it was through like a mini Keen thing on our campus. So we had some of the 3 C's. This was making these connections between the equations that these students see and use in homeworks, but the underlying concepts and real world behavior that these equations are helping us try and understand or model. And so I tried to think about a couple different ways of doing this. Lab courses are, the kind of quintessential example of giving students hands-on experience to get to try out and apply knowledge in kind of real-world situations. Unfortunately, for our particular curriculum, our lab was offset. So we have biomaterials and biomechanics taken in the second year, and we have a combined biomaterials and biomechanics lab that comes after the fact. So students get to play around with deforming materials and measuring and calculating all these things, but not until after they had finished my course. So I know it needed to be something inside that's the lecture course based setup. This idea that I'm going to present, I had originally kind of formulated as an in-class demonstration just to save on material costs and times. So I basically did what I eventually had the students do, but I did it up front with some student volunteers. And it basically had no impact whatsoever on the students' ability to answer that question on the final exam. So then what I did is I decided, okay, I'm going to bite the bullet, buy more of these supplies, and devote an entire class time for the students to actually go through with this kind of hands-on experience. And so what I ended up doing is providing students with these rubber rods that can be purchased from McMaster-Carr. So McMaster-Carr sells them. They have lots of different kind of cross-sectional areas, as well as a couple different stiffnesses that you can buy. And I passed them around to the students, and I said, first, your task is to try and figure out, are these rods made of the same material or are they made of different materials? And so at first I asked them to, just manipulate these, make some hypothesis based off of pulling on them, seeing how they deform, seeing what kind of force is necessary, propose some hypothesis for if you think these are the same material or different materials. And then I actually had students go through in what is a pretty, low-tech, simple experimental setup to actually collect kind of data from some very, again, low-tech tensile test in order to quantify the deformation and hopefully try and answer that question of, are these the same material or are they different materials? So what that looked like was, in this case, I had students work in groups of 3. This was mostly like 60 students, 20-ish kind of sets of these components. It does, again, the way I had delivered this, it definitely was at least a 2-person job. So you couldn't have it done individually. But I had it done in groups of 3. I would provide all of these materials to the students. I would give them calipers and rulers so they could measure the dimensions of their kind of specimens beforehand. And then we had these kind of very simple metal holders and weights from some other labs that we had run that I had adapted. And I basically had students hang weights from their supported rod. And then with every new weight, they would literally just measure the new change in length. And then they would repeat this, adding different amounts of weights, and they would do this for all 3 of the different rods. And then there was basically a guided problem set that helped them with, guiding them through collecting their data, organizing it, processing the data, and then going through that analysis. And then I had them submit that assignment for a grade. So it ended up being an extra graded assignment. I won't show you the whole problem set, but just very quickly, right? So there are some places to just streamline recording their data, what weight was hanging off of the different rods, and what was the new length. There was the instructions for, how to go about, reminding them, okay, you're going to need to convert to stress and you're going to need to convert to strain. These weights are in kilograms. Make sure you convert to force instead of mass. All kind of the various simple instructions to give to second-year students. And then there was a section to basically guide them through analyzing their results and a brief discussion. So what was their initial hypothesis? I had them and very explicitly plot both their force first deformation curve and their stress strain curve. And again, the goal here was for them to tangibly see and create themselves that graph from the textbook, where the exact same material that's in different dimensions, your force first deformation curves are very different. You can't tell if they're the same or different, or you're likely to think that they are different. But when you convert them to stress and strain, they now converge, and you can tell that they are actually an identical material. And then they would have to do a simple linear fit and then report the Young's modulus and use that information to basically arrive at some conclusion of, are these the same material or are they different materials? And then compare back to their hypothesis that they gathered from just their kind of tactile-based analysis of that. And there's a couple discussion-based questions. The big one that I kind of really wanted to drive home is having them actually say, all right, look at these two graphs, right? Your force versus deformation graph, your stress versus strain graph, which is more useful in terms of trying to understand material properties. With the hope that they talked about, or recognize that for the force deformation, which is essentially what they were experiencing when pulling on it, that you are conflating both geometry and material properties, and that by normalizing to your geometry with stress and strain, you can actually understand that you're getting just the material and testing condition aspects, and normalizing it to lots of different potential contexts. So in terms of the actual implementation, this was a 75-minute class. I ended up using the full 75-minute class period. So definitely, again, did have an impact on, theoretically, the amount of content over the whole semester I could deliver. Definitely did not require 75 minutes, right? Most students were able to finish it in 15 to 20 minutes of actually collecting the data. And then a lot of them stayed to do the analysis and kind of basically finish the problem set, but they also left. So again, very easy to implement in a shorter period of time if you wanted to. It was an extra graded assignment that students got feedback on, which again, both has, positives and negatives. Positives in terms of one more way for students to practice the content that they were learning and get feedback on that, but did add an extra kind of grading burden for the instructing team. I had my TAs grade it, which helped with that. But it did seem to lead to, again, pretty substantial improvement on that conceptual understanding. And this is by no means like a scientific study in any regards. This is just that exact same question presented in the exact same format on the final exam, the year when I did it as an in-class demonstration, and this year where it turned into a whole lab, and saw pretty significant improvement on the performance for that question, where at least my best attempt, kind of post facto of trying to account for any differences in student population, there was no real difference in overall exam scores. So can't necessarily say it was definitely this activity, but I tried two different ways where students basically kept getting in the 25% range. And after implementing this as like a thing where students actually had to do it and got a grade on it, it led to this improvement. It also was relatively well received by students. I had a little just like Likert scale survey that I gave to them, basically saying how enjoyable was it and how useful did you find it? And it got, right around the 4 out of 5, which is typically what I see for interventions that students don't mind doing, or like as you get around that 4 for both useful and enjoyable. So overall seemed to be relatively impactful, and definitely something that I am no longer teaching this course, but luckily the current instructor is having me come back to continue to deliver it. So hopefully we'll see if it continues to be useful to them. A couple kind of issues that arose or areas for improvement is there was definitely, I think, some trouble with measurement and precision. It was not necessarily clear where you should start and stop measuring in terms of, what point you used. And I think students would occasionally have, as they were deforming something, it wouldn't be exactly very precise. And so it did end up, whereas when I did this myself, I got this nice convergence of all 4 curves. A lot of times the students would still have some slight differences that led them to say that one material was different than another because of some measurement and precision. And then the other thing, and this is, I think, probably true of any lab-based class that you would deliver to, especially second-year students, right? This understanding of what is natural variability and what is not, right? Students would see, a 5 to 10% change in Young's modulus of one of them versus the others, and they would say this one is clearly different. And obviously, I think that's a whole extra really important learning objective, to talk about what is natural variability and understanding when you can draw conclusions about things being different and when you can't. Wasn't really any feasible way for each group to do like replicates by any means, but could potentially have the class average together and get some amount of standard deviation or standard error, and then incorporate some idea of either statistics or at least just recognizing what variability is and when you can say something is different versus when you can't. So overall, some kind of minor things that made it not work exactly the way that it had worked when I was doing it, that I'm looking into thinking about how to improve moving forward. So future changes. This was actually a recommendation that I had gotten when I presented this at ASEE that I thought was really great. Right. So instead of saying, are these rods made from a different material? And they're not, and it felt like a somewhat forced kind of curiosity-based question. Instead, purposely including one of that set of 3 or 4 rods that is a different stiffness, and then now giving them what is likely a more realistic question, which is, one of these is different, figure out which one it is. And hopefully that is, again, a little bit more of a authentic kind of problem to be tackling. But also it hopefully addresses for that natural variability. How can you tell what is different or not? If one of them now clearly has a different slope than the others, hopefully that will help them kind of recognize that a little bit more tangibly. So that's something I'll be trying when I deliver this semester. The other thing that we will try to do, and this is related to that measurement and precision of exactly what points do you pick as your start and end point with which to measure your dimensions, trying to find a way to add some kind of lasting markings to these rods so students clearly know where they are starting from and where they're ending from for their measurements, and it's hopefully a little bit more consistent, and therefore their measurements are a little bit more precise. So we'll see how that works moving forward, but those are just some changes based off of that previous iteration that I'm looking forward to using. So that was all I had. Again, pretty low tech, quick, simple, hands-on experience. Hopefully clearly useful for people who teach some kind of deformable materials class that isn't tied to a lecture or isn't tied to a lab, and therefore you can't necessarily have that inbuilt hands-on activity. But if nothing else, hopefully just an example to maybe spur some curiosity or creativity about how to think about in a lecture-based class where you normally can't do hands-on data collection and stuff, how you can try and think about designing something that gets at some aspect of troublesome knowledge that the students might normally be missing with just lecture slides or in-class activities or equations. So I'd be happy to take any questions, comments. I know there's discussion. I'm happy to talk more about this. And again,